Today we're going to be talking about atomic structure. We're going to be looking at the development of the models of the atom, going from the ancient Greeks to modern theories. So let's begin our journey thinking about how the models of the atom developed, what we thought we knew, and what we think we know now. So the early models of the atom came from the ancient Greeks. The ancient Greeks thought that there were only 4 types of matter. Anybody want to guess what those were? So those were the classics. The ancient Greeks thought all matter was made of 4 elements: fire, earth, wind, and water. Now, can this really explain all of matter? Let's think about it. Fish were water and fire because they were alive. Things that were alive had the breath of life, which was the spark of life, which was fire. Worms would have been earth and fire. Fire would have just been fire. I mean, it's really hard to get all the different types of matter using just these 4 elements. So we're going to move forward, huge jump in time, to Boyle. Robert Boyle in the 1600s identified that silver and gold were not made of any of those classical Greek elements, and thus he said those are their own elements. Because silver and gold were certainly of great concern. They were the basis for most monetary systems in Europe at the time. He ushered in what we consider to be the era of modern chemistry or modern atomic theory. Now, we're going to move forward a little bit further to John Dalton. Now, Dalton's model of the atom was pretty simple, and these dates that you see here on the screen, they don't refer to when Dalton lived and died. That was when he was actively working on his theory. So he was an English teacher and a chemist. Now, he wasn't a teacher of English. He was from England, so he was an Englishman who was a teacher and a chemist. He was the first individual to propose the existence of the atom as we think of it today. He considered the atom to be a single solid particle. Think like a cue ball in a game of pool. He wanted the atom to be a single, hard, solid sphere. And there's our John Dalton. He looks like a very serious fellow. Now, Dalton came up with some laws because this was the time of creating laws. You had Newton's laws, now we have Dalton's laws. Dalton said, all matter is made of atoms that cannot be broken down. Well, that's still kind of true. All atoms of an element are identical. More or less, but we're going to dive into that later on when we get into something called isotopes. He said all atoms of different elements have different properties. 100% spot on. Good for you, John Dalton. He said atoms are neither created nor destroyed. Once again, once we get into nuclear chemistry, this gets a little loosey-goosey, but we're going to let it slide. We're going to hold on to that for now. And compounds are formed by the combination of atoms of different elements. Good work. So these were Dalton's laws. All matter is made of atoms that cannot be broken down. All atoms of an element are identical. Atoms of different elements have different properties. Atoms are neither created nor destroyed. And compounds are formed by the combination of atoms of different elements. So we're going to move a little further in time to J.J. Thomson. J.J. Thomson was working in the 1890s, the late 1890s. He was a British physicist, and he used a device called a cathode ray tube in which a voltage was run across 2 electrodes or 2 wires. You guys probably aren't familiar with cathode ray tubes now, but old TV sets, if you see the old huge ones that are like a big box with like a curved front, those ran on a similar cathode ray tube that when electricity moved through it, it would glow. He ran electricity across 2 electrodes or wires. And when this happened, he saw a glowing beam of particles traveling from the negative end of that cathode, that's called the cathode, to the positive end, which is called the anode. You might have heard these two terms used when people talk about batteries, but if you haven't, that's no big deal. We'll go into that again as well. So using magnets, he determined these particles had a negative charge, and he also determined they were very tiny. I don't know if you could hear that, but a huge plane just went overhead really low. Wow. Okay, so this was Thomson, once again, another very serious looking fellow, and this was his cathode ray tube. It had a metal plate in each end, a negative end and a positive end, and a stream of negative particles flowed from the positive cathode to the negative anode. The tube was filled with a gas that when exposed to electricity, it would glow. So here is his cathode ray tube. Now let's dive into this a little deeper. So the cathode ray tube was filled with a specific gas. It wasn't filled with air. And when he ran electricity through it, that beam of electrons went from the negative end to the positive end, made a beam appear. And this positive and negative business is going to be really important to us later. He turned it off and the beam went away. So turning it on made the beam appear, turning it off made the beam go away. So now we're on again. So our beam is going from our negative end to our positive end of our cathode ray tube. Off, no beam. You get the idea? So it was flowing from the negative end to the positive end. And he got this idea, well, if it's going from negative to positive, what's the old adage about opposites? Think magnets. Opposites attract. So he thought if it's flowing from negative to positive, which means it's going toward the positive, the charge on the whatever is happening in the tube has to be negative because opposites attract. So to explore this a little further, he had an electric field with magnets. And what he saw was that the beam of light bent toward the positive magnet that he was exposing the cathode ray tube to. And this confirmed that the moving pieces, whatever these particles moving through this tube were, they had to have a negative charge. If they didn't, if they had a positive charge, they would have bent toward the negative magnet. So, based on this theory, he thought atoms are a big cloud of positive charge with lots of tiny particles of negative charge floating in them. And he called this the Plum pudding model. So here in our picture, we have our spherical cloud of positive charge with our little red dots of electrons floating in it. Now you might wonder, why was it called a plum pudding model? Well, Thomson was English, and a really popular dessert in England at this time was the plum pudding. Now this isn't pudding like we necessarily think of pudding in the United States, but a pudding in England was a steamed cake, kind of like a fruit cake. So if you think of a fruit cake, it has all little bits of fruit inside it. You can see where he got the plum pudding model. We might, in the US, call this a chocolate chip model or a raisin cookie model. Take your pick. Pizza pie, knock yourself out. I don't know how Thomson would have felt about the pizza pie, though. He's making me nervous. I gotta move on. So that covers part of it. But what about the rest of the atom? So Thomson basically said, here are these negative things in electricity. Maybe those are electrons. So we've got electrons. We know there's a positive charge somewhere in the atom as well. Where do we go now? Now, Ernest Rutherford worked in Thomson's lab with radioactive alpha particles, which are smaller than atoms. Basically, they're a helium nucleus that has a +2 charge, but Rutherford didn't really know all those details. He just knew they were positively charged and a little bit on the heavy side for a radioactive particle. Now, he took these alpha particles, once again, that had a positive charge. This is going to be so important to us. And he shot them at a very thin piece of gold foil, essentially a piece of gold leaf, just a couple of microns thick, to see how they would behave, and he thought they would go straight through or be slightly deflected. Well, let's look at what he found. And here's our friend Rutherford. Once again, serious looking fellow. What's with all the mustaches? I don't know. It was England, 1890s. It was a thing. So here's what he did. He took a lead block and he drilled a hole in it. And in that hole, he put a little bead of polonium. Polonium spontaneously goes through nuclear decay and emits alpha particles. He then aimed that polonium beam, or that alpha particle beam, at that very thin piece of gold foil, and all around it he put a fluorescent screen, essentially a piece of photographic film or X-ray film that would darken when exposed to the radioactive particles, just like photographic film darkens when you expose it to UV light. So here's what he thought was going to happen. He thought the beam would go through and hit the other side and make a dark band of exposure on our film. If this happened, it would prove that atoms were mostly a diffuse positive cloud with a few little negative charges in them, because there would be nothing for that beam of alpha particles to hit. So he said the alpha particles were going to pass through without changing direction very much or at all. And he said this is because the positive charges are spread out so evenly throughout the atom that they alone are not enough to stop the positively charged alpha particles. Remember, charges are important here. Positive charges and other positive charges are going to repel. They're not going to be attracted to one another. So once again, what he expected, beam goes straight through, exposes on the film, you get a solid band of exposure because all those particles are going to go straight through that gold leaf. Well, he thought, once again, this is because mass is totally evenly distributed in the atom. There would be nothing for them to hit that they would be attracted to or repelled by. But here is what he got. So that's not at all what he expected. And the exposure on the fluorescent film was completely scattered. You had all these ricocheting alpha particles going everywhere. Now, lots of them did go straight through, but some of them got deflected, meaning their path of travel was bent. Well, why would this happen? Any ideas? Well, he got to thinking. He said, okay, so some of them passed through. Some were slightly deflected and some were very strongly deflected. And he was really surprised by that strong deflection because it didn't make sense at all according to his hypothesis. If the small positive charges were scattered all over the atoms in a cloud with little pockets of negative. So he came to a conclusion about density in the atom. Said since most of the particles went through, the atom has to be mostly empty. Empty. Because there was nothing for them to hit. And because the alpha rays were deflected so much, the positive things it was hitting had to be really heavy. So whenever you have a really small volume and a big mass, that would equal a really big density. I don't know. Don't go around telling atoms they have a big mass. I'm just saying. Rutherford said small volume, big mass, big density. But he also said the atom was mostly empty. And that's when he had his brilliant breakthrough. That small, dense, positive area in the atom had to be the nucleus. And this is where we get our first mention and first idea that there is a nucleus in an atom. So at this point, we've got Thomson bringing the electron to us and Rutherford coming up with the nucleus. Now notice, he hasn't called anything a proton yet. That's going to come along later. But he has said we have this positive, heavy nucleus. At least it's heavy compared to the rest of the atom. So in the Rutherford atom, he said, we have this kind of circular area. There are negative charges scattered through it, just like in Thomson's model. And we have a positive, heavy, dense nucleus. Now, let's move into modern times. We're getting to Niels Bohr. Now, Niels Bohr's model shows a dense nucleus with electrons around it in orbits. Now, this brings us to Niels Bohr and his planetary model or solar system model of the atom. And chances are, when you think of the atom, this is kind of what you're picturing. In fact, I have this model essentially in the logo on my channel. Because once we go beyond Niels Bohr, it's kind of difficult to conceptualize what the atom actually looks like. So this is kind of where we sometimes mentally get stuck. His model shows a dense nucleus with electrons in surrounding orbits. The first energy level can contain 2 electrons, and the second energy level has a maximum of 8 electrons. And we're going to go into energy level and electron shell configurations later on when we do discrete structures of the atom. But right now, we're just sticking to the basic models. So this was Niels Bohr, 1913, so we're about 15 years later than Thomson and Rutherford. He said we have neutrons and protons in our nucleus, and the electrons orbit around them just like planets orbiting the sun. They're not confined to a planar orbit like the planets are. There's more motion involved. And there's a much older looking Niels Bohr after the whole, nuclear energy, his theories being used to build bombs thing. Not good. So the Bohr model of the atom kind of looks like this. We have a nucleus in the center of the atom. Okay. We have electrons in orbits around that nucleus. Those orbits are distinct paths that the electrons travel in, and they stick to them. They don't go anywhere else. And we have energy levels of orbits. Just like you have individual orbits for the planets around the sun, these energy levels would act in the same way for our electrons orbiting around our nucleus. Once again, the nucleus has the proton and the neutron in it. We'll get more into that later. And so you get something like this. Now, the planetary model, once again, protons and neutrons in the middle, electrons around the outside. And when we're looking at this, it's pretty easy to conceptualize. You can picture this. But that's not how atoms are. That's not how atoms work. It's an oversimplification. Just like Dalton was an oversimplification, Thomson was, and so was Rutherford's model. Doesn't make them bad. They just didn't have the ability to conceptualize these parts of the atom because technology was limited for them. Just like in 1,000 years, a lot of our theories are going to be perhaps seen as pretty primitive because technology will have gone so much further. So at this point, we're going to discuss the quantum mechanical model. Sometimes the quantum mechanical model is called the electron cloud model, the modern model, or the orbital model. And it's based in the Heisenberg uncertainty principle, and we're just going to touch on this just a little bit. So the quantum mechanical model, which is where Bohr went later when he was working with Albert Einstein, is that the electronic structure of the atom deals with the probability of finding electrons within certain regions of space, known as orbitals. So at this point, we're abandoning the terminology orbit and we're going to the terminology of orbital. Orbit, old, orbital, new. So the modern view says that the atom is mostly empty space. Thanks, Rutherford. And it has 2 regions. You have the nucleus, and that's where your protons and neutrons are, and the electron cloud, which is a region where you might find an electron. Now, let's take a second and go to the Heisenberg uncertainty principle. This is the idea that electrons can behave both like particles and like waves, and that's where we get the name wave mechanical model. The problem is that if you observe them acting like a particle, then you can't see them acting like a wave. And if you see them acting like a wave, you can't see them acting like a particle because you can only observe one or the other. And by observing it, you potentially change it. And it's this whole mishigas. And maybe we'll talk about Schrodinger's cat, but not today. So orbitals are regions where electrons with a particular amount of energy are likely to be found, kind of like a cloud or a puff of dandelion fluff. So let's review the models of the atom and look at each of these models and see if you can tell me which one was theorized by which scientist. If you need to go back and watch another section of the video, please do. So our 1803 model, that would have been Dalton. Our solid sphere model. Our 1904 model would have been the Thomson model. I know it's a bit hard to see, but you have our tiny little electrons scattered in our pink positive cloud. Our 1911 model would have been our Rutherford model because look there, look in the middle, so tiny, so precious, so dense, the nucleus. Our 1913 model is our Bohr planetary or solar system model. And lastly, 1926, we have the advent of the wave mechanical or the modern model of the atom, where our electrons are in clouds, which are regions of space where you're probably gonna find an electron. So my question to you now is, does an atom look like this? Bohr thought it did, but like any good scientist, based on new information, he abandoned this model and went to the wave mechanical model. That's the way science works. You have an idea, you have a hypothesis, you test that hypothesis, making the best observations using the most current technology you have available. And then a few years later, you have new technology. There are new observations that you can make, and you revise your hypothesis. You change, you develop, you evolve. So that was the history of atomic models. I'm glad you stuck with me. And in our next video, we'll be talking about the structure of the atom.